Okay, so let me just give a couple of applications of this long division business. Okay, so this long division, often called the division algorithm, is a very important statement regarding polynomials. It has all kinds of very nice consequences. So for example, if so, here is the first application of the division algorithm. Let f of x be a polynomial and let a be a root of f of x. Let a be a root. Okay, a is a number, you could assume it is a real number or a complex number and so on according to the case. A is a root of f of x, then f of x can actually be written as x minus a times some other polynomial times q of x for some polynomial q. In other words, if f of a is 0, then f can always be written as x minus a times something, it is a multiple of x minus a. So observe, if f has this form, of course if you substitute x equal to a, you will surely get a 0 because there is a term x minus a in front. Okay, the key content here is really the converse, that if f of a is 0, then f must be a multiple of x minus a. And let us prove it just using the division algorithm. So let us do the following, let us take, so how do we prove this fact? So let us just take g of x to be x minus a and just apply the long division or the division algorithm. It says when you divide f by g, f of x can be written as g of x, which is x minus a, times a quotient plus a remainder, okay, where what is the property of the remainder? The degree of the remainder, so either the remainder is 0 or it is non-zero and has degree, it is non-zero of, okay, with degree of the remainder being strictly smaller than the degree of the polynomial g. Okay. Now observe, g is just a polynomial x minus a, so it has degree 1 because that is the highest power of x which appears, degree of g is 1. So of course this must be a 1. So what does that tell us about the degree of the remainder r? It can only be a 0 because the degree is strictly smaller than the degree of g, right. So there is only one possibility for the degree is always 0 or higher. So therefore we conclude that either r of x is 0 or r of x has degree 0. Now what does a degree 0 polynomial look like? It has only got a constant term, right. Remember it looks like a0 plus a1x plus a2x squared and so on, but if it has degree 0 it means it only has a constant term a0. Okay. So it is basically a constant. What we are concluding from here is that the remainder is a constant, it is either a 0 constant or possibly a non-zero constant. The claim is it is in fact a 0 constant, it can't be a non-zero constant. Why? Because we have some fact about f. We know that if you plug in x equal to a, f becomes 0, right. So now observe that if I plug in x equal to a, the left hand side is f of a, which is a 0, so what is given about f, whereas the right hand side becomes the following. If I plug in x equal to a, of course this term becomes a 0, so it becomes 0 times q of a, which is a 0, plus r of a. Well, r is just, you know, it's 0 or a naught. So let me take the second case. I claim that this case can't really appear, so plus this remainder a naught. Okay. Now we just look at what both sides are. The left hand side is 0, the right hand side has a 0 in the first term plus an a naught. So a naught had better be a 0. So we conclude from here that a naught is actually a 0. Okay. So what does that mean? It says that the remainder can't really be a non-zero constant. We conclude that the remainder is 0, so that tells you that f of x is just x minus a times q of x. You do not have any remainder term there. So that is exactly what we wanted to conclude. Okay, so that's the first application. So we have just completed the proof of that. The second thing here says if f has degree d, if f of x has degree d, then it has at most d distinct roots. Then so a polynomial of degree 10 for instance can have at most 10 different roots, okay, it can't have 11 or 12 or anything higher than 10. So let us see why this must be true. So here is a proof of this fact. So let us write down all the roots. So or let us say suppose we know some number of roots, let x1 x2 till xl be roots of f, let them all be distinct. Okay, so I am looking at different numbers, be distinct roots of f. So now we use the first application where it said anytime I have a root that polynomial, if a is a root then x minus a divides the polynomial f. So f can be written as x minus a times something. Okay, so we just do the following, we write f of x. So since x1 is a root, we conclude f of x is divisible by x minus 1, x minus x1 times q of x, right. So because x1 is a root, so let me write this down, x1 is a root of f of x, implies f can be written in this way. So that is what we just concluded. Now let us plug in x2 into this equation. If you plug in x2 for x, then f of x2 is 0, x2 on the right hand side you will get x2 minus x1 times q of x2, and x2 is not equal to x1. So observe, so the second conclusion the following, since x2 is a root of f of x, it actually implies that it must be a root of q of x as well. x2 is a root of q of x, okay, because x2 minus x1 the term in front is non-zero, which means again you use the same thing. It says since you know you have a root of q of x, x minus x2 divides q of x. So let us call the quotient as something, let us call it q1 of x. Okay. Now what do we get? Putting these two things together, f of x is x minus x1 times q, q is x minus x2 times q1. So putting these together you conclude that f is actually x minus x1 times x minus x2 times this polynomial q1 of x. Now again the same thing, I have a third root x3, I plug in the third root here, I get f of x3 is 0, I plug it into the right hand side, I get x3 minus x1 times x3 minus x2, both those are non-zero terms because x3 is not equal to x1, x3 is not equal to x2. So these two are non-zero, so therefore it must be q1 of x3 which is 0. Okay. So again we conclude the same thing, so x3 being a root of f, so f of x3 is 0, therefore implies that this quotient q1 must have x3 as a root. So again you do the same thing, therefore x minus x3 must appear in q1, you can write it as x minus x3 times something, let us call it q2, and now you keep proceeding. At every step you conclude that a term of the form x minus x3 will divide the next fellow, x minus x4 will divide the next fellow and so on. So you keep going and conclude as at the very end of this process that, so keep going, finally what do you conclude? Keep pulling out various factors like this all the way to xl times some some quotient, let us call it let me call it g of x. That is the final quotient, the quotient I get at the last step. So finally this is my conclusion. Now observe that again it is the same degree argument. On the left hand side f of x has degree, so what is the degree of f of x? So degree of f of x is d, that was the assumption. Whereas the degree of the right hand side, observe the right hand side has well, how many terms does it have? There are L terms here and then one more, which is another g of x. The degree of the right hand side, abbreviate to RHS, is nothing but, remember the property, if you have a product, the degree just adds up. So I have each of these factors has degree 1, so it will be 1 plus 1 plus 1, I have L such ones plus the degree of g. So whatever this is at least L, okay. So the degree of the right hand side is at least L, whereas the degree of the left hand side is exactly a D. So what do you conclude from here? Hence, since the left hand side and the right hand side are both equal, you conclude that D must be, D is the degree of the left hand side, and so that is at least L, because the right hand side is the same as the left hand side. So degree of the RHS is the same as degree of the LHS, which is D, so D is at least L, that is the conclusion, okay, and that is exactly what we wanted to conclude. So this was our claim that you can have at most L distinct roots, okay. Okay, so this just one final thing before we end this small lecture. This has one very nice consequence, a different way of rewriting the same thing. It says a polynomial of degree D is determined by its values at D plus 1 points. So view it as another application of the same thing. A polynomial of degree D is uniquely determined by its values at D plus 1 distinct points. Okay. So it is like saying if I know that my polynomial has degree 3, then if I know the values of the polynomial at 4 points, any 4 points, distinct points, then the polynomial is uniquely determined. You cannot have two different polynomials which have the same value at 4 points. Similarly, we already drew an example of a polynomial of degree 2. We drew the graph of that polynomial, we saw it was a parabola, okay. So in general a quadratic polynomial will have a graph as a parabola. So one instance of this is like saying the parabola is uniquely determined if you just tell me what its values are at 3 given points, okay. So if I just tell you the value at this point, the value at this point, and say the value at this point. So through these 3 points here, so let us call them A, B and C, there is a unique parabola passing through the points A, B and C, okay. So sort of a one simpler version of this is, if I have a polynomial of degree 1, its graph is a straight line, okay, and a straight line here according to this, a polynomial of degree 1 is uniquely determined as soon as you tell me its values at 2 points. So that is like saying there is a unique straight line which passes through any 2 given points, okay. For a parabola you need 3 points that will determine the parabola. If you have a cubic curve, a curve of a degree 3 polynomial, if you give its values at 4 points, it uniquely tells you what that curve is, okay. So this is something that we will start out looking at in the next module.